Selamat hari kayak gini. Dapat hasilnya mass integration. Talking about mass in this topic, uh, what thing integration, pinch analysis, and case pinch analysis. I think previously the Dr. Farid transfer is focusing more on heat and energy. So, but it's how to optimize water in the process as well as the gas. I'm Dr. Khairul, chemical engineering. My background is chemical engineering, bachelor engineering, chemical engineering from prestigious Pahang. They further study PL 2010, finished 2021. Let's finish in 2012. 2 years. Bioprocess engineering, coursework. But for the first project, did work with water filtration, specifically ultrafiltration. The swim I studying doctorate 2018, finish in 2021.
Sorry, doktor.
Yeah,
Uh,
can you hear me?
Mek Arang saya dapat dengar suara doktor gila sebabnya putus-putus.
Okay.
Ah, I think doktor Sempu might ada problem kah?
Thế là cho muốn đâu mạch tôi rồi. Thế cho vào rồi mình cũng sẽ tội lên. Sẽ thật rồi.
Masih putus-putus.
How about this one? Is it okay? Masih betul-betul tak?
Yang ini okey?
Okay, ya.
Itu okey. Okey, doktor.
Thank you. Okay. So for my doctorate, focusing on photocatalysis. So the word photocatalysis means the catalyst can be activated through light. Normally, when we do the reaction, chemical reaction, normally we need heat that could happen. So in my case, we harness the light for water treatment as well, specifically for phenol. It's normally found in pharmaceutical industry. The moment, I hope you can hear it. At the moment, focus is I still do the water treatment, mainly on ultrafiltration, but the scope is widened. We have done heavy metal removal, dye, what else? Uric acid, treatment of the pit water. But since last year, we diverted to my group, diverted to other branch of research. We're now focusing also on hydrogen. Specifically, we try to fabricate or develop a new method to produce the hydrogen without an electron. So far, we successfully obtained the hydrogen, but in terms of efficiency, is too low, less than 1%. The highest we get is below 2%. In order to make it commercially viable, at least we need to reach 10% efficiency. And when compared with electrolysis, especially the solid oxide, can get up to 80%, or even the alkaline electrolyzer can get to 70%. But for research, this is what we do. We do the fundamental study. At the moment, we already file patent for 2 methods. The first method is for the water treatment, how to make the membrane transparent. Instead of normally we see membrane, it's white color normally, like a plastic or paper. Another patent is for the synthesis of the catalyst to replace electrode. We call it an electrodeless hydrogen production. That study is another 2 years to be completed. Still in the synthesis part, we have I have 3 students working on it. One PhD, one RA, then the other one is undergraduate. For the membrane this year, focusing on ultrafiltration. The project we collaborate with the Indonesian, how to treat water from the groundwater. For we done the analysis for the groundwater, it's many things inside. And some of it is, of course, the heavy metal. So this one for the introduction. So for this course, I was told to prepare one final exam, one question is already submitted last 2 weeks ago. It's later you in them, but something to do with the cascade analysis. But before we go to the technical, we should start with the fundamental first, which is what is mass integration. Actually, I thought I want to start with the history, the mass integration, so that you know why it's better and how come you need, why you need to learn it. For the past the two lecturers before me, focusing on the energy. So for the energy, it's actually the pinch analysis method. It started with the heat, which is under energy. Then it widened to the mass integration or the mass pinch analysis. We call it. Yeah. But this method is until 1994 first method. Yeah. I believe it's 1994 by, I have the paper and the image. We can check it out. Paper number 1, Westport Terminalization by Wang and Smith. It's 1994 paper. I believe this is the first clearly explain what pinch analysis. Although in this case they didn't coin the term, but they use wastewater minimization. But this this method is actually is a pinch analysis. So this is slide number 1. I also share with you book 1 and book 2. Both will not cover everything inside the book, but some part of it. Let's start with the first book. Book 1 can refer to chapter 10, page 353. Not sure how does the microphone work or not. It's water pinch analysis for water management and minimization. An introduction by Professor Sharifah Rafidah Ahmad Alvi and Professor Zainuddin Abdul Manan from Prospect UTM. This two professor is one of the prominent professor or expert, we can say, in water pinch analysis specifically. Let's see what this is. I think how we do did you learn water, not water pinch lah, because normally in chemical engineering the student only learn about heat pinch analysis. So, if one of you have prior knowledge about pinch analysis in general, besides what the two lecture previously explained. Okay. So it's not really different, but the idea is there. The principle is, let's say, the same. Because for pinch analysis, normally we use heat. Normally we need to do the magic element, then identify the flow rate. Normally we given equation. But in final year student for our course, need to come out with the design of a plan. So to design a plan, they need to come up with major value to identify the heat or Q. From the Q, then you can do the pitch analysis. So in this case, it doesn't require heat, but it require the flow rate. That is the difference between mass integration and heat integration. So in mass integration, the flow rate is between water and the contaminant. The water doesn't necessarily to be doesn't necessarily a clean water, meaning water from the municipal or the pipe water. The water could be coming from the process itself, but the purity is not that up to clean water purity, but it's enough to treat the contaminant. So approaches for water management and minimization. You may refer to page 353. You can stop me anytime. Have question. So both of the processes introduce what management hierarchy. You can refer to figure 10.1, the book. So this figure consists of 5 levels that are ranked from the most preferred option to the least preferred option. So this preferred option you see here, fresh water. So for the water integration, water pH analysis, we try to avoid fresh water. Although if we use fresh water, everything will be soft, but there are disadvantages or drawbacks. Mostly it's about cost. So the more fresh water they use, they need to pay much more. So what we do, we try to regenerate the actual water. This is what happened in the key number 4. So we regenerate the used water from the process itself. To regenerate it, we need to install something. So that something is like that because we need to, the water has been used, then we need to regenerate it. We need to clean it. We need to remove the pollutant from the water. How do we do it? What you do, there are many things. Later we learn how. It's up to complicated process just to regenerate. All it doesn't necessarily, but you need to do it for cases like hydrogen. Sorry, for the gases. Gases is expensive. So yeah. So for the water, for the regeneration part, You can use absorption, B absorption, or Youngman filtration, or just a sand filter. For the third one is the direct use. Later you will learn also how to direct use the water. But for the direct use of water, the purity of the water to be reused must be must be better than the water that it want to uh, clean. Or outsourcing. Outsourcing means the rainwater harvesting. You can also use river water for the cleaning. But to use river water, unless the water is good, doesn't have any, have least contaminant, then yes, you can reuse it directly. Reduction and then elimination. Elimination means you don't use the contaminant at all, or you don't produce the contaminant at all. How you do it? Instead of using this specific chemical, what you do is you use another type of chemical which will not polluted the water stream or the process, or you reduce the amount of the pollutant or contaminant. How you mix it with something or pair it with something that have the same, say, the same purpose. So the increasing purity, the best way is eliminate. If you cannot eliminate, then you reduce it. Then you reduce the current process stream inside the process itself to remove some contaminant. Or you need to regenerate or recycling. Regenerate first, then reuse this again. Or if all of this cannot use it, sorry. If you cannot do any of the one until four, then the last method is to use the fresh water. Oh, regeneration. Regeneration refers to partial treatment of wastewater or even external water source to match the quality of water required to further use. There are two possible processes of regeneration. Regeneration exactly use the wastewater in the same treatment. That's after treatment. We have regeneration reuse, which involve reuse of treated water in other element after the treatment. We can see this in article 10.2, book number 1. So for the first case, oh, this is actually this advanced. They redraw it from the paper by Wang Slip. To refer to paper number 1, believe I have you can see this thing is available. Yeah. Although the drawing is not that good, because this paper is 1994. Yeah, the use typewriter. But The idea is they can refer to page append. Yes, page 183, page number 3. It's okay. So this is the process one. Then you produce the water. You see wastewater already contaminated. So what you do, you need to regenerate it and use it for the process two. This is the regeneration and reuse. The third one is the regeneration and recycling. So you have two processes. So the incoming water goes to process one and process two. So the incoming water here, normally this is the fresh water. This is fresh water, fresh water. Then the wastewater, you regenerate it. Some of it goes to the water treatment. Then the regenerated or clean water. The term clean water from the regeneration doesn't necessarily it must be 100% clean. It could be 70% clean, so meaning there are 50% contaminant inside the process. It can be that way. It depends on the process one, process two, and the requirement. Then it goes back to the fresh water to the stream. This is mixed with it. So the water after the after the mixing from the regeneration, it must be within the acceptable limit for both process one and process two. So there will be an emission from the regeneration. So instead of example 70% only clean, so it be the liquid could be up to reaching up to 90%. So freshwater usage, level 5, should only be considered when wastewater cannot be recycled or when wastewater needs to be deleted and recycled very quickly. So the or when the wastewater needs to be deleted to this is what we see in figure. Figure 10.2 C. So the regenerate water being diluted. Not that was what has of budget when you go discharge the line. Use of freshwater is the least desirable option from the water minimization point of view and is to be avoided whenever possible. So since you are learning about water integration, so we try our best to minimize the amount of freshwater used in the process. Whenever you do the whenever you do the design for any new process, put in mind as well that it can be used the water from the previous process of channeling fresh water just to that new process. Water footprint reduction. So for the water footprint reduction, this one you can refer to book number 2, chapter 5. Chapter 5 here in the book 2 is page 105. So water footprint is a concept that expresses the measure of how much fresh water is used during the life cycle of a product. So water footprint consists of elements known as blue, green, and gray water footprint. It, you also know it as gray water. What is green and blue water. So grey water normally we know about it. What is a grey water? It's actually water that has been used. We usually use it for cleaning. So yeah, then that water is considered a grey water. There are also black water, although it's not inside here. So black water normally we don't reuse it again. We just treat it, then just release it. So for the black water, normally for the domestic use is water from the toilet. So the rainwater footprint is in the consumption of rainwater in soil. The blue water footprint, if you refer to this book, the book number 2, right? Page 109 there. The virtual blue water content of the product is the volume of surface water or groundwater that evaporate as a result of production. For example, the evaporation of irrigation water from field irrigation canals, storage reservoir, which is what we call as blue water. Is it clean? Yes, it should be clean. It's water evaporated, like a uh, condensation. You see, in the rainwater, it's clean, but uh, but when the rainwater reach the soil surface, it collected many this contaminant, so which is why it's not clean, but it's clean after. It's blue water. So dry water for clean is the volume of the polluted. Let me read from the book. The virtual green water content of a product is the volume of water required to dilute pollutant in order to meet water quality standard for reuse reuse or discharge to the environment. Okay. In this case, a volume of water polluted. It could be from industry, from agriculture, or from domestic use. Yeah, we can treat it back, then reuse it. Maybe not for washing, for the water in the domestic use, maybe for something else. Later, there are interesting case study in the UTM, how they treated the grey water from the moss, and they reuse it for something else. Blue and blue and grey water footprints that can use are calculated using the chain sub method. The blue water footprint of the product is calculated with the total amount of water during the process and the collection amount. Blue and Hmm. So WF product equal to WF products equal to the key bracket is not certain amount. WF product here is a given per kg of product. WF product S bracket is process water liquid water consumption per year. Here is number of process step. The grey-water producers are producing wastewater flooded and COD not the facility. WF process grey, which is LMIC net C max per product. So here is the to the volume. So WF process grey-water grey between per kg product. The L is the bulletin what the kg of the product. CMAX is the maximum water quality standard. The relevant pollutant, then the natural concentration of the receiving laboratory. Okay. So the water footprint is one of the most commonly used indicator. And what's the water use assessment? The table 2022 represent the characteristic of the WF and compare the WF with other post-assessment tools. We have life cycle costing and optimization tool, which is water pinch analysis. The comparison of water resource assessment and the design tool. So for the water footprint assessment type, it's a cost assessment. The life cycle costing also cost assessment. For the water pinch, it is in-process targeting and design. So what does it mean by post-assessment? Meaning something that has happened, you do the meaning the data is used or collected is actually happened already. So from there, you do the water footprint. Even the life cycle costing is also the same. Life cycle costing, okay, we have it. How about the water pitch analysis? So later you will learn that it's we do the although the process already started, but from the process which is online already, we do the water pictures. Meaning from the data from the process, we do the pitch to optimize the water use or water reuse. Then come up with a new design how to optimize the water. Okay. Yeah, this is like determination of water quality. The volume of water needed to improve the measurement of oxygen content in the system. Fluid are considered as the constraint. The composition is not satisfied. Yeah. Next is the life cycle costing. Is just life cycle costing. The concept of life cycle costing was initially developed by the US Department of Defense and applied in the UK and the US several decades ago. The LCC, there are two terms. Later you will learn also LCC, but the one LCC is is for the water pinch analysis. This LCC is for the life cycle costing. This is just introduction slide. We learn the fundamental first. Later there are also LCC, but the LCC is the limiting composite cost in which you have you how to use it. Then for the water regression, water pinch analysis. The LCC was designed to account for the total costs expended in support of the item and conception and manufacturing implementation. In the end of life, the concept was mainly applied in the industrial segment for product or construction assessment. Due to the comprehensiveness of the method, it was challenging to be implemented as it required an enormous amount of data on the whole life cycle of the distress item. Therefore, in practical implementation, what are the cases are just part of the lesson. So, the word life cycle, you need to understand. So, let's say it's a product. So, the product life cycle is from its raw material, and from the raw material, it's processed to be the end product, which is tire, for example, from rubber to tire. So after we use the tire, then we need to change it. But the old tire, the life cycle is still there. What happened after that? So one of it is to reuse it again, or not sure how, but that is the life cycle, meaning of the life cycle. So now that we discuss or coin the term of what let's say the circular economy. That one is, we can say it's a life cycle. So meaning from tire, reuse it, then discard it. That same tire, we need to do to use it for some other thing, just to close the loop. So there will be less space if we adopt the circular economy, the life cycle method. But for water, it's challenging because yeah, it's a lot, and it's not just a lot. There are many use of water, although it's coming from the same source as a fresh water. But after that, there is a process inside. It will be regenerated, it will be reused. Then what happened after that? The same water, does it being reused again or just regenerated, then become the wastewater, goes to the wastewater treatment, this is why it says here it's changing the bioenergy data on the whole life cycle cycle. Okay. Pinch analysis. For pinch analysis, you can refer to book number 2. Book number 1 is the same. Talking about the same thing. Let's see what book number 2 explain. Pinch analysis was first developed for page 113. Book 2. Pinch was first developed for his exchange network synthesis and subsequently extended to yield other energy integration application. The analogous characteristic of it must transfer allow the application of pitch analysis to the synthesis of mass exchange network. I think previously you heard about heat exchange network or HEN from previous lecturer, hopefully, because they are covering energy or heat. So in my case, it's a mass exchange network and a series of other mass regression problem. For water pinch emerge as a special case of mass integration following the seminal work of Wang and Smith, paper 1. However, that paper targeting technique was limited to the fixed load problem, where water using process are modeled as mass transfer operation. The later work on water pinch analysis has focused mainly on the fixed flow rate problem, where flow rate requirements are viewed as the important constraint for water using processes. Okay. So compare with post-assessment tools such as water footprint and as well life cycle costing. WPA or water pinch analysis is a design and optimization tool for industrial water use. So WPA if you refer to book number 1, they refer the water as the mass separating agent. Page 355, section 10.2. So the fundamental principle of WPA was introduced by Wang Smith. Same thing, developed based on your approach of mass sensor. Okay. So the mass exchange network, the first paper is by El Halwagi. Is the general approach of mass exchange network, not really a water. It's just a mass established by El Halwagi and his author in 1989. In this case, water is assumed as a mass separating agent or lean stream that function to remove impurity from the rich stream, also known as the fixed flow rate problem. So this include process such as absorption, solvent extraction, and vessel cleaning. Okay, this is some history of WPA. Just a bit. 1996, Dole et al. Introduced a new version of water pinch analysis, which cater for other water usage such as water consumed and generated in a reactor and water losses, also known as the fixed load problem. Milan has splitter. Okay. So this new version of WPA by Dole in 1996, it separate the water source, the demand using data extraction Instead, WPA technique has gone through various improvement and extension from these two angles. So WPA propose okay. So WPA mainly include two types of approaches: insight-based case analysis and the mathematical programming-based targeting method. The insight-based uh, technique mainly include graphical targeting technique like the material recovery pinch diagram and algebraic targeting techniques such as material cascade analysis. So the word material here it can be water, gas. Yeah. Some book they use mass, and some book they use material, but it's the same. It can be oxygen cascade analysis, hydrogen cascade analysis. A typical WPA solution is stop lah. A typical WPA solution has two steps of setting the water target and followed by network design to achieve the target. So in the work by Wang and Smith, paper 1, target of using fresh water, maximizing water reuse and water regeneration are discussed, and both single and multiple contaminants are addressed. The composite curve are used to represent the water using process. So the word composite curve, this is uh, the LCC for the pinch analysis. The approach LCC in pinches is the limiting composite curve. The approach that identify the bottleneck with the minimization and industrial processes. The conceptual framework can have specified optimal type generated in respect. So their work referred to the Wang Smith. It's one of the earliest contribution of graphical methods to recognition study using WPA. If you refer to paper 1, okay. If you refer to paper 1, it's quite a thick paper. First paper, sorry, first page, reuse. If we exclude the possibility of making fundamental changes to process to reduce their inherent demand for water, there are three possibilities of sorry, there are three possibilities for reducing wastewater. So, kalau satu kau habis kejap. First one is the reuse. Wastewater can be reused directly in other operations, providing the level of previous contamination does not interfere with the process. Although you can reuse the wastewater, but it must not interfere with the process. The one you can refer back to the figure 10.2 in book number 1. There are three processes. So process B and C, which require regeneration there. So the regeneration for the water use must not interfere with next process using the water. Reuse might require wastewater being blended with wastewater from other operation or fresh water. So the word blended here means does it blended kan ya? Ada. The word blended here means you dilute it. Dilute it. Dilute the contaminant up to certain percentage of certain concentration that allow it to be reused for the next process, and that incoming diluted wastewater is actually will not interfere with that process. Okay. Not the not that there may be recycling maybe. Within an individual operation, but here we consider only the net input and output from the operation. B, if you refer to the paper page 1, you're okay, 1, 2, this is 2 Roman, regeneration reuse. Wastewater can be regenerated by partial treatment to remove the contaminant. Why we need to learn this? Because later on, when we do the case study, what else? When we do the there are a few methods for the pinch. So instead of using fresh water, it will solve the problem, but it will incur costs. So then we need to understand the term regeneration, reuse, regeneration, recycling, plus reuse. So for regeneration, reuse, wastewater can be regenerated by partial treatment to remove the contaminant, which would otherwise prevent it reuse, and then reuse in other operation. Again, reuse after regeneration might require blending with wastewater from other operation or fresh water. Let us emphasize that when water is reused after regeneration, in this case, it does not re-enter process in which it has been previously been used. So water from process 1, you reuse it, which require regeneration. So this water cannot enter the process it's coming from. It must be reused for another process. In comparison with the recycling is the water from process 1, you regenerate it, then recycle back to the process 1. For regeneration reuse, it's process 1, incoming produce the wastewater, goes to the regeneration part, then water from the regeneration part diluted with fresh or other wastewater goes to the next process or process 2. You need to understand the term. Yes, gradually akan complicated, but still can be learned. Regeneration recycling, already explained. So this paper will develop method to target and design for minimum wastewater for the above 3 cases. Although we will concentrate, for example, from petroleum refining, this is based on this paper tahun 1994. The methodology example in the paper, it's lean toward petroleum refining. But the method can be used in other type of operation or industry or process like pulp and paper, textile, dye stuff, pigment, and steel. As long as it's require it produce wastewater, then we want that wastewater is not considered black water. Then yes, we can reuse it again. We take a break first. It's 1 hour already. We reconvene, I think, another 10 minutes. Welcome back. This is targeting minimum wastewater for single container. We're still discussing the paper one, right? This is the third page, the paper one. Consider the water using calculation figure 1A, which is figure 1A put in the paper. The process material is contaminated with water in order to reduce the level of contaminant. So the contaminant is coming from here, and the outlet is here. So this the water. Doesn't necessarily clean water or fresh water. It doesn't say in the, but the water here, the purpose is to remove the contaminant from the processed water. The processed material is contacted with water in order to reduce the level of contaminant. The water in turn become contaminated. This, for example, a petroleum refinery desalter in which crude oil is mixed with water to extract salt from emulsify water in the oil. The oil and water, so here the sea process out is oil with water inside. So the oil water are then allowed to settle with the assistance of an electrical field as separated into pieces. Figure 1B. So for the figure 1B, it's still the same process. Petroleum refinery desalter from figure 1A. This is the interpretation of the based on the concentration. So y-axis is concentration, x is the mass. So in example of the desalter, the contaminant would be salt. Salter. So the contaminant is salt. So in practice, the mass transfer in the desalter involves a number of contaminants, but we will not address the problem until later. If you refer to this paper, the belakang, this is very good paper. Well, cover many things, including the paper report. But we will learn about the inlet and outlet station in the process stream are specified by the process requirement as established of Figure 1b show one spell combination of inlet and outlet concentration water to satisfy the mass transfer requirement, specifying the inlet outlet concentration of water and the mass transfer as well specified the water correction. What can you the figure 1b? So the concentration of salt in CW India, you see, it's here instead of here. What does it mean? It's in there, CWN, water is actually contain a bit of salt, but still lower than the salt concentration for the process. Meaning the water in this process is not actually using the fresh water because it's using the fresh water. The sea should start at this 0 because we know already now the contaminant is the salt. So the C here refers to the concentration. So for the C in going into the desalter mixed with the incoming process stream, which have a high concentration salt. So it's exchange. Then the concentration of salt, which is lower, because decided by the CW in, but in this case CW in or water inlet, the water of the concentration of the salt is sama, very similar at the end. Because it's a so this is what happened in figure 1 in water plus central decrease. The C process concentration decrease. Figure 1C. Clearly, different water flow rate is of the same flow rate in figure 1C. In order to maximize the possibility water reuse from other operation to this operation, so the word reuse is means that the water from process 1 previous process goes through this result. This case, simplify this. We should classify this points when you refer to page 2. We should classify water with the highest possible inlet concentration, then specifying the maximum possible outlet concentration minimums water flow rate at the maximum inlet concentration. What is what? For figure 1C, this is the incoming water profile. Because the water used from other operation S. So there are several water inlet. If you refer to figure 1P, only one word. So this case, we want to reuse from other operations. So there are several water profile, but still the concentration of the process is higher than the water profile. Then specifying the maximum possible outlet concentration minimize the water flow rate at the maximum inlet concentration. In figure 1D, this water profile shown in figure 1D will not necessarily be the profile we will use. The final design is simply represent a limiting case. We will therefore design this to be the limiting water profile. So any water supply line which is below the limiting water profile will meet the requirement of the system. If you refer to figure 1C, so any water profile that is below the limiting water profile, that water profile can satisfy the can be reduced to dilute or to treat to remove the particular what the profile means. So what happens if the water profile is higher than the limiting water profile? Meaning the arrow is higher than this and the limiting. So if it lies above the limiting water profile, then the water profile, sorry, yes, the water profile from other process, it cannot be reused and it require treatment like the process itself, or can be discharged to the wastewater treatment. That's all. Either you treat it if you want to reuse it, or you can just discharge it. How about the water profile below the limiting water profile? Then one you can just reuse. No need further treatment. I hope it's clear. So if the water profile is above the limiting water profile, what you need to do is to regenerate the water profile. The word regenerate means you need to treat so that it will not it will not affect the petroleum refinery design. So that the requirement for the waterfall, once it's above the limiting waterfall, you need to treat it so that the arrow is lower than the limiting waterfall. So any water supply line which is below the emitting water profile will meet the requirement of the process. Okay. Figure 1E shows two examples. This is 1D. Figure 1E shows two examples of different water supply lines which will satisfy the process requirement. The maximum inlet outlet concentration for the limiting water profile may be fixed by a number of possible concentrations. So if you refer here, so these two water supply line, which is this water is coming from, if you see here, this water supply line, this arrow is actually a fresh water. This line is actually reused from the process. So both of these, because it is below the limiting water profiles can be reused for the process. So the maximum inlet and outlet uh, concentration for the limiting water profile may be fixed by a number of possible consideration. So, keyword here is the limiting water. How do you get this line? The limiting water profile that can satisfy the there are a number of possible considerations. The first one is the minimum mass transfer value cost, which might vary between different processes. We have a maximum solubility. The need to avoid precipitation, solution volume conversion, and minimum flow requirement to avoid settling of solid material. Possible consideration. Example 1. This is from the table. Consider now a simple example involving a single contaminant. We will use this to first illustrate the basic approach of setting target for one product. So table 1 is 1, 2, 3, 4. This is the mass lot of the contaminant. Based on this example, the mass lot will refer to the amount of the chloride for process of contaminant here is salt. So the concentration for process 1 0 ppm. Salt is 100 ppm. Then we have a system. So also in table 1, we assume that the mass transfer is a linear function of concentration. This is usually valid in dilute system. However, if the behavior is significantly non-linear, the approach can still use for representing the non-linear process as a series of linear segments. So figure 2a shows plot of the limiting water profile of each equation in table 1. So we have four operations, four process from the table 1, you see 1, 2, 3, 4. So each process is individually represented in figure 2a is A. So process 1 you see here concentration 0 until concentration 100, in which the mass lot of contaminant is 2. Then we have process 2. So for process 2, it started at 50. And up at 100. The US node is 5. Next is the process 3. Stated at 50. 50 ke 50. The first 50 is 50 is the conduct. The last one is the next. So this graph, yes, we refer to the percentage. So ppm is a unit of percentage. Is equal to the milligram and 1 ppm. 1 inside the ppm we also pb. ppm refer to part per million. pp is pb. Figure 2b shows the design which corresponds to parts. Corresponding water flow rate would be 1.2 with the equivalent per hour. So fresh water 1125. That's what the one. Proses one berapa banyak ke? 2 1 1 is so if we are to estimate the water flow rate overall, we must analyze the how the water process using process behave. For this, we can construct the limiting composite curve. Limiting, this is the limiting composite, the LCZ. First part was limiting water profile, limiting curve. In figure 3e, the inlet and the outlet concentration of the processes define concentration interval within each concentration interval. Within each concentration interval, the rate of mass transfer is constant. Had any of the process exhibited significantly nonlinear mass transfer behavior, they could have been represented by a series of linear segments. It would have created additional interval at the point of intersection of the segment. So from here, banyak data, but actually the arrow here is coming from the table 1. See here, for the first process, this is arrow for the first process, which is moved from 0 to 100 ppm. Then the second process, starting from 50 to 100 ppm. The third process from 15 to 800 ppm. And the last one is 400 to 800. So draw the meeting water. By combining operation within concentration interval, we obtain the limiting composite curve in figure 3b. The limiting composite curve represents how the total system would behave if there were a single water using process. The idea of a concentration composite curve was first introduced in 1989 El adapted from the temperature enthalpy composite curve of Linhoff. Okay, this one is just explanation. So what happened here is combining. So meaning from here, although the angle is like this, just combine it. This is straight figure versus 3 goes up from here, goes directly process 4. Then we have the composite curve. So that is the limiting composite. For figure 3C, show the water supply line match against the limiting composite curve. The inlet concentration of the water supply line has been assumed to be 0. So the water supply line assumed to be 0. So meaning the line for the water supply line must start at 0, C equal to 0, which is fresh water. By maximizing the outlet concentration of the water supply line, fresh water use and hence wastewater generation are both minimized. In this example, the minimum wastewater line touches the limiting water profile both at 0 concentration and intermediate point where the supply line touches the limiting water profile create a pinch the design. In general, there will normally be at least one pinch. So from here, we draw the water supply line tangent to the limiting composite curve. So the point crosses the limiting composite curve. This is the pinch. Let us emphasize that because the water supply line touches the limiting water profile, this does not mean they have a zero mass transfer driving force at that point. At the pinch, the driving force goes to a minimum. Since the minimum mass transfer driving force has been put the data, alternatively, the decision at the pinch rather than being minimum mass transfer driving force not leading to correction. So from figure 3C, we identified that the minimum water flow rate, for example, for the example, single limiting contaminant. So single contaminant is 90 ton equivalent per hour, compare with the 112.5 ton equivalent. Figure 2 reduction of liquidity. So if you refer back to figure 2C, 2B in the paper 1, you can see previously the process require around 112.5 ton equivalent per hour of fresh water, which is a lot. So since we do the pinch, actually the minimum water flow rate for example 1 is actually 90 ton equivalent per hour compared to the 112. This is a reduction of 20%. For this target to be meaningful, we must be able to achieve the target flow rate in a design in which the concentration do not exceed the maximum inlet outlet concentration and feature the same mass level as the intended one. Okay. Oh, okay. So how do you obtain the 90 ton equivalent per hour system calculation? So 9 kg per hour here multiplied by 1 million ppm divided by 100 ppm. When you get 90 times 10 to the power 6 kg per hour divided by 100, you get so why 1 million? 1 million because of the part per million. So the highest ppm is 1 million. That's the reason. Activation and fish analysis. Right. So now we turn back to book 1. WEPA or water proof analysis can be defined as a systematic technique of implementing water minimization strategy through integration of processes for maximum water efficiency. In production term, the pinch refer to limit on productivity or bottleneck. In terms of mass recovery, pinch occur at the smallest driving force that limits mass recovery bottleneck for mass recovery. Okay. So this is based on book 1. So they assume that water is the mass separating agent. It's the function to remove impurity from the rich stream. So the rich stream, also known as the fixed flow rate problem, which include absorption, submersion, and vessel cleaning. The new version of the WPA separate the water source and demand during data extraction. Since then, WPA technique has gone through various improvement and extension from these two angles. WPA proposes for wastewater to be reused in a process that require less pure water instead of being discharged to wastewater. So the basic message from of WPA, this is from paper Tange and Rutman in 1999. Don't solve an end of pipe problem with end of pipe solution. Unless you have explored the in-process solution, your end of pipe solution could be the worst solution of your problem. So what does it mean by the end of pipe problem? So in this case, example, you have this wastewater. So the water is already filtered, so you cannot discharge it. It could go beyond the limit of the water discharge. So what you have to do is to treat the water. This is talking about end of pipe, meaning the water already used goes to the wastewater treatment. So within the wastewater treatment, you propose a method to treat the water. So one of the method is using filtration or membrane filtration. So by doing membrane filtration, yes, that produce a good or clean water, meet the requirement for the filtration. But by using the membrane or filtration in general, you create this concentrated pollutant before the discharge, because the pollutant cannot go pass through the filtration, so it remains there. So once it's remain there, then how to treat the pollutant? It keeps increasing in concentration. That is what does this sentence special mean. So in the end of pipe solution, although in short period it can solve your problem, but for the long run it will create another problem, which is worse than the previous. The significance of water pinch analysis. It is generally easy to identify potential design improvement on existing plants and utility system that can yield good investment payback. However, it is difficult to be sure if the proposed scheme are the best for a given process. Quite often, technologies working on an improvement retrofit project is left with the nagging doubt, can I do better? Even until today, progress made in in-process design has largely based on the learning curve as shown in figure 10.3a. 10.3a. Okay. So this is method. The first method is the design or retrofit based on the previous method. So here is the initial. Then from the initial, the company do improvement, which contribute to cost saving, but the increment is only here. Then next year, the following year, they have this new method. Improving from the previous method, yeah, they can increase up to. So it's actually gradually increase, right? Still 1 to 2 to 2, 3, and so forth. So each line require a design or a retrofit with the existing process. Unlike pinch analysis, so you have a previous data 1, 2, 3, 4. So from the previous data, you can do the analysis for the pinch, in which by the fourth process of fourth improvement, we do the pinch target. So it can be increasing up to here. So you see the step changes, step change here compared to gradually increasing. So this is the traditional method. This is the So the technologies would quickly use a previous achievement. This is this method. So by doing this method, although there are improvement, but the improvement is relative to the previous design. So the increment is not that much. If you were to increase from this point to the second or sorry, for the third point, then you need to do the second method, the pinch target. A true minimum target should be based on the specific structure, operating condition. Determining on the plan undergoing a profit instead of common of a similar plan with elsewhere. This is where efficiency has a key advantage. With the notion of true minimum design target at available in analysis, technologies would be less likely to settle for marginal movement. What's try to achieve the true minimum? This is the true minimum. As a step change in, as a step change in improvement. Okay. So this is why we do the pinch analysis. Before this, we learn about the term that will be used in pinch analysis. This is the reason why we need to do the pinch analysis to set the cost It was a sudden jump in the improvement of the projection. Now, mass speech is first step of mass speech analysis. This is the general step for mass speech analysis. The first step is plan audit on mass network. To analyze the plan work of the targeted resources through plan auditing. So the first step here is to gather information about the plan network. Or other word, we refer to the drawing, the PID drawing, PFD drawing. Because from the drawing, then we do audit on the mesh network and collect the data. Because for the mesh speech analysis, you did a flow rate. So you need a flow rate. Unlike heat speech analysis, which require you to extract the heat information. Next is the data extraction. Identify the water source and sink the targeted resource with the potential to recycle and reuse. So what the keyword here is the water source, the water sink. So the water source refer to any stream that provide water for reuse or recycling within the process. So if this process one, so the water coming out from the process one, so that water, if the water is for reuse to other process or recycle to its own process, that is the water source. Where is the water source? After the process one. So water sink. So water sink is any process option that require the water input. So from process one, if the water to be reused, the process one, then goes to the process two. So process two is the water sink. The process one can be also the water sink if the water is recycled back to the process one. So the water source is outlet, water sink is the inlet. That's all. Water sink inlet, water source. Because later on, this term will be kind of hard. Need to understand. So the target minimum resource. Target minimum resource. Determine the minimum fresh resource required for the analyzed network. Kalau ikut buku, the book number 1, page 357, the data extraction, second step. The second step is the water source, water sink, having potential for reuse and recycling, and to extract the limiting water flow rate and limiting concentration data. Non-limiting concentration in the water system are situated at the concentration below their maximum limits and do not affect the water sink for that operation. The third step is setting the minimum utility target or target minimum resource. The third step, establish the minimum possible quantity of fresh water requirement and wastewater generation or the minimum water target using a targeting method. I don't know this. The fourth one is water network design or retrofit. So the fourth step is to design a water recovery network to realize the minimum water target. So once you identify the pinch can be coming from certain process. So that certain process, once we identify the pinch, then we need to normally we need to redraw the PID or PFD to cater the water recycling or water reuse from the certain process that in which the pinch happened. The last one is the economic evaluation. The first step is to evaluate the economic of the water network. We are still learning about the fundamental. This is a part really. Don't think so. But yeah, we have another 4 weeks and 3 weeks. Not 3 weeks. 3 class. Flow chart for mass pinch analysis. Oh, chapter. Chapter. So this is the first step. For the alignment, visible design, stop the filter in design mix and full constraint. It's known and goes to evolve to the design again. Okay. Oh, plan audit on mesh network. This is based on book one. Okay. Good candidate for implementing water saving project include process unit, making high value product process unit. They are large water user. Unit relating high toxicity waste, plant site with poor water availability or rising water costs. Then set undergoing expansion, process unit or plant site with disposal problem. Start with tightening water regulation and plan with plastic constraint in the wastewater treatment facility. Okay. So this is the some of the reason. If you want to implement the water saving project through water pinch analysis. So in implementing the water pinch analysis for a plant, the overall water network of the plant should first be obtained from the process flow diagram and the process instrumentation diagram, PNID. The water mass balance is conducted for all the water stream. The mass balance data can be obtained from existing material balance, computer monitoring, routine measurement. Okay, this is where you get the data. It's all in step 1. Choose first the project based on that list. Water mass balance is conducted for all the stream. Note that in general, water using equation can be classified into 2 main categories: a mass transfer base and the non-mass transfer base, and MTB operation as follow. Okay. For the mass transfer base operation, an MTB water using equation is characterized by the preferential transfer of species from a rich stream to water which is being utilized as a lean stream or an MSA. This can be clearly assisted by the using a mass exchanger block diagram as in figure 10.4. This figure. So the water or the lean stream. So water here is the mass separating agent. Goes in, then the process stream, the rich stream, rich with the contaminant goes inside the transfer of mass. So the concentration here should be higher than here. Should be. So this is the mass transfer base operation. So the mass transfer occurs here. The delta M. So it's transfer from the rich stream to the lean stream. The 2 major examples of MTB water using operation are cleaning and absorption. Cleaning involves the preferential transfer of species or contaminant from a rich stream. In this case, the equipment being washed to a lean stream or MSA, in this case, water. Figure 10.5a shows the water used for the cleaning process as a sink and wastewater generated as a source. So this is the cleaning, vessel cleaning. So remember, the incoming is the sink. This is the water source. The sink, water source. So what happened? Water, clean water goes inside. So inside the vessel, it's dirty or full of contaminant. So once it's clean, the water source here is lot of contaminant. So the best transfer occurs inside the vessel. Next is the B, 5B, 10.5B. For the absorption process, water is the MSA or mass separating agent, and is used to remove contaminants such as H2S, hydrogen sulfide, and sulfur dioxide, sour gas stream. Note that the input and output flow rate of a mass transfer process are assumed to be the same. Hence, this type of operation is also known as a fixed flow rate problem. So water goes inside. So they are delta M, meaning they are mass transfer occurs inside. So the sour gas do the mass transfer, pollutant goes to the water. So here the sweetened gas, clean gas. So this is the water sink, water source. Beside MTB, there are NMTB, which is the non-mass transfer based operation. And NMTB, water using operation cover function of water other than MSA. An example of such an operation is water being used as a heating or cooling medium where there is no mass transfer involved. For such operation, sometimes only water sink or water source exists, as shown in figure 10.6. Water in okay. So water goes into the system but is lost as it evaporates in figure 10.6. So this is the cooling tower. So two common type of an MTB water using operation, boiler and cooling tower. So for cooling tower, fresh water goes in, then it's evaporated out. Next is the boiler. So in figure 6B, in the boiler, the water is generated from the condensation of the steam. There's no water inlet, but only water outlet from the condensation. Another example, as in cases where water is being fed in as a raw material or being withdrawn as a product, a byproduct of a chemical reaction. This is also an MTB. Refer to figure 10.7. Water as a heating or cooling medium or as a raw material fed into a reactor is not intended for preferentially transfer species within stream, hence it's fairly represent non-mass transfer operation. So if you refer to figure 10A, 10.7A, the water is in it's a pit material, but the inlet is sorry, the outlet is there's no water because the reaction occurs inside. This is a reactor. So this reactor consume water for the aniline production. Similar to, not similar, but for 10.7B, water only exists at the outlet. So the reaction between oxygen, ammonia, and the propane. Mm, to produce acrylonitrile. So the byproduct is the water. Next, so those water source and sink stream having the potential to be reused need to be identified. So from now you have learned about type of methods for type of operation. Then you learn about what the sink of the source. But how do you know that what the sink and the water source is suitable for the process? Let's say you identify the concentration, but how do you quantify the concentration? So to quantify the contaminant, we can use analysis method, such as COD, chemical agent demand. We have DOD, total suspended solid TSS, total organic compound TOC, and total dissolved solid TDS. That prevent direct use in the water with limit into the process and within the wastewater going to be the three most important key contaminant are normally chosen. According to Sabansky, this is page 361. So several measures exist to assess the quality of the discharge water. We have TOC, BOD, COD, tadi TSS, TDS. So for example, TOC, BOD, COD, this one is for the organic matter content, because the O in the TOC, BOD, and COD refer to the organic. For the oil and gas, for oil and grease and total petroleum hydrocarbon, give a measure of the presence of the oil, grease, and other hydrocarbon. Several physical characteristics of wastewater include the TSS, pH, temperature, color, and odor. So to determine the concentration, it doesn't necessarily the actual concentration, because normally in plant, the wastewater have little contaminant. So how do you measure the quality of the water? You need to conduct like not specific to the contaminant, but the overall quality of the water by using COD, BOD, what else? TSS, TDS, pH, temperature, meaningful. This is just to give the idea how you quantify the quality of the, the water source. Okay, hydrogen distribution. For refinery hydrogen distribution, the three typical process involve a hydrogen consuming process, hydrotreater and hydrocracker. Hydrogen producing process or catalytic reformer. hydrogen purifying process, separation, separation, and cryogenic separation. So catalytic reformer, this is using the petroleum, fossil fuel, hydrogen production. All of these processes are in MTB operation, and hydrogen fall under fixed flow rate program. In general, the process stream of process unit are the source stream, where the inlet stream are the demand or sink. Okay, new keyword is the demand, water demand. So water demand and water sink is the same, meaning you have the process, the inlet is the demand or the sink, outlet is the source, the source. Step 2, bawah step 2. Step 2, data extraction. After analyzing the water network, the water process are grouped into plant section. Process chosen are properly close geographically and are also chemically related. So within the process, the process plant, each section there are certain section which refer to which require there's using similar chemical within the section, and it is within the section. It's not that this part is here, this part is there. It's very long. Then if we do the pitch later on, the pipe will be very long. This is why we do the data section. The main contaminant that prevent direct reuse in the water system are chosen. The system can be modeled either as a single contaminant or a multiple contaminant approach based on the water quality requirement of the plant processes. However, the problem of multiple contaminant involve complex modeling procedure and relies on mathematical modeling and optimization technique. An alternative, okay, that's it. Okay, this one. So the system can be modeled either as single contaminant or multiple contaminant based on what we call the process plant. But the problem with multiple contaminant, because we address, if you remember table 1 in paper 1, the table 1, the C is only one component, which is sound. If we have multiple component, we address it individually, meaning you have several tables for each of the contaminant. You see how the graph later on, the chart C over M, there's a lot of arrow because this is a multiple contaminant. But it's, although it's a multiple contaminant, it is within one stream, is part of the composition of the stream. So alternatively, what we do is to use the aggregated contaminant method, such as a suspended solid or an TDS, that allow multiple quality factors to be modeled in a single contaminant. So in order to avoid the multiple contaminant approach, so we quantify the multiple contaminant not as contaminant but as aggregated. It's combined together. and quantify as a suspended solid. Total reserves. So the modeling of aggregated convenient as a single is known as a pseudo, nama lainnya lah. Pseudo apa? Pseudo single contaminant system. Sebabnya sebenarnya. Because it's not really a single contaminant, it's just more analysis single contaminant. So they call it a pseudo single contaminant system. The proposed network then need to be reassessed by checking that all other contaminant concentration not considered are still within allowable limits before implementation. The entire water sources and zinc fluoride impurity requirement for each water process, each water using process are extracted. The water source data are obtained by identifying the maximum concentration limit and the minimum flow rate limit, the wastewater source for each process. The water sinks data are usually obtained from historical variation, emergency water substitution. Estimate from engineers, vendors, and operators, and description and equipment list. So you understand already what the source is, where you get the water source. What does it mean by the water thing? Oh, pada. Step 3. Setting the minimum utility target. After extracting the relevant data, water targeting can now be performed. Methods that have been proposed for minimum water targeting are as follows. So we have a few methods in this book. Even in this book is a lot of methods until 7, I think. Yeah. Oh no, 6. We have 6 methods proposed in this book. First one is the limiting composite curve, which you have seen in paper 1 just now by Wang and Smith. Then we have water cascade analysis. So this method, numerical version of WSD, water surplus diagram, that eliminate the iterative process and provide a more accurate result. So the water cascade analysis, the term coined by the author of this chapter, Professor Zainuddin. Then we have sourcing composite curve. This is by El-Halwagi in 2003. So the water sourcing are plotted on a contaminant mass load versus flow rate diagram. Was introduced by El-Halwagi for the material recycle or use. But later, Prakash Nishino in 2005 introduced a similar method for the water system, which the later claim has been published earlier in their student thesis. The sourcing composite curve overcome the limitation of WSD, which require to graph an iterative process applicable for both fixed flow rate and fixed load problem. So for the water surplus diagram, the one you need to refer to. Books, page 362. This is by Halale in 2002. So the water sourcing are plotted separately and on a concentration versus flow rate diagram to determine the water surplus and deficit. The water surplus and deficit are then summed to form the water surplus diagram, WSD. The freshwater target are then predicted by using trial and error until all the WSD lies on the right hand side of the y-axis. This method is applicable to both fixed flow rate and fixed load problem. Wow. Let's see for the NCC person. Okay, NCC already. This is the same. This is the same example from the paper one. Wang and Smith, 1993. Okay, we do the WCA water cascade. This is still under step key. Setting the renewability title. For the water cascade analysis, go to page 363. So WCA is a numerical targeting method with the aim of establishing the minimum water target. The overall fresh water requirement and wastewater generation for a process after looking at the possibility of using available water sources within a process to meet a water sink. To achieve this objective, the net water flow rate, water surplus, and deficit at different water purity level within the process and the study has to be established. So for the water cascade analysis, you are required to come up with the table later. So from the table, we do the cascading. The word cascading is macam tahu. It's like a step. Yeah, okay to do, but it's require the information from previous stream to calculate the stream, the next stream. Then the next stream require the previous stream information to calculate it. So the way we calculate it, it's like a cascading into bawah, which is the term water cascade analysis. Conceptual illustration of a minute. Finish 10 minutes before. Conceptual illustration of how water cascading can minimize fresh water leak and wastewater emission is represented by figure 10.9. This is the figure 10.9. So for figure A here, figure 10.9A, 100 kg per second of wastewater is produced by a water source at the purity level 0.999 or 100 ppm, and 50 kg watt per second water is needed by a water sink at the purity level of 0.998 or 200 ppm. Without considering water reuse, 100 kg per second of water will be generated, while 50 kg per second of water would be required. So meaning these two process is not, let's see, it's not related. Yeah, it is related, but it's not. There's no connection between these two process, which is why the process one, we can say this process one, producing 100 kg of wastewater. Process two is require 50 kg of the wastewater. However, as shown in figure 10.9d, this figure, by making use of 100 kg per second of the water source at purity level 100 ppm, to satisfy the water sink of 50 kg at purity level 200 ppm, it is possible to avoid sending part of the water source directly to the effluent, like this, at 100 ppm. Doing so not only reduce the wastewater generation, but also freshwater consumption in both cases by 50 kg per second. Okay. So from here, instead of the inlet or the 100 kg per second goes straight to the wastewater treatment, it is being reused for the second process. How come you can reuse it? Because of the limiting concentration here is less than the concentration from, say, process one is lower than the limiting concentration from the process two, which is why you can just reuse without the regeneration. So by doing this, we only require we only produce 50 kg per second of wastewater. So what else in being reduced from this process is the amount of the fresh water. So the amount of the waste is reduced by half to 50 kg. We don't need the fresh water for this case. So this is the water cascade. This is just the gist of it. Yes. A general structure of WCT, or water cascade, water cascading table, or water cascade table. It's a water cascade table, WCT. The first step is setting up the density is to list all the contaminant stations of the water using processes. Remove duplicates if any and set up the contaminant station table in an ascending order as illustrated in the first column of the table 10.2. So the first column of the 10.2 is the concentration. We also call it the contaminant concentration, mass load of the contaminant, but all of it is referred to the contaminant concentration. So in this case, process 1, 2, 3, 4, and 0, which is the fresh water. Next is the second column, which is the PVT. So here later kita explain next week lah. Si cukup rasa nak explain lah. This table. Panjang sultan. Ada ada 9 kot. So if you have any question so far, later we continue water cascading analysis lah. Water cascade table. Any question you can ask me straight away or through chat or email can as well. Those who haven't checked in, check in. Can check in. Separate. Thank you. Hope you learn new knowledge today. Next week we continue about the water cascading table. Then what else? Some case study. I think it's possible. Some case study next week for the water cascading. Sure. Okay. Thank you.